All right. Chapter 11 deals with the development of the history of quantum mechanics. So we're going to just continue that. And then once we see the history of quantum mechanics, the historical development of quantum mechanics, then we'll try to apply it to chemistry. So, quantum theory started with observations, and the observations were unusual observations. That is, if we make a light bulb, in a standard light bulb, we excite the electrons, and the electrons don't stay excited forever. So we excite the electrons. Eventually, the electrons will relax back down to what we call the ground state, their ground state, which would be a lower energy state. And in the process, they're going to emit that energy. And they emit the energy as light. And so sometimes we can excite it to low energies, like red light, or high energies. And if we have a whole spectrum of energies in which we excite this, then we'll have a whole spectrum of colors that we'll observe from this light bulb. And if we have all the colors of the rainbow, all the colors of the rainbow add up to what color of light? White light, exactly. Mm-hmm.
So you said that the white light is where the electrons are moving a lot, and then the electrons go back to not vibrating as much, and then it's visible light?
Yeah, right. It could be that they aren't vibrating much at all, and then we get infrared light. What's missing here is if the detector extended out here, you can't see it, but the detector can feel it. And so beyond red, we're going to have infrared, which is lower in energy, and above violet, we're going to have ultraviolet. But we don't see those. You could feel those, like the infrared, you could feel the ultraviolet. You can feel the damage caused by ultraviolet light. And so quantum theory, quantum mechanics started with unusual light patterns, and the unusual light pattern is this. Here, what's unusual about this is there are a whole bunch of dark regions, and these dark regions correspond to forbidden energies. So when you excite the electron can't get excited to any energy. It has to get excited to very specific energies. These are called discrete energies, or discrete or allowed energies. And then we have a bunch of forbidden energies. We see lines not just in the visible, but there are lines in the infrared on this side of the red, and then there's lines in ultraviolet on this side of violet that you can't see, but you can detect using detectors. And not only that, the light looks different. In a hydrogen lamp like this, it's not emitting white light. It's emitting this kind of purple glow, and that purple glow is a composite of these four colors here. And so this is where quantum mechanics starts, at least the development of quantum theory. And so after observation comes what? Like in the typical scientific method, you start off with observation, and what's the next step? Patterns. And we see a pattern here. You see a red, green, blue, violet pattern here. But there's a color pattern, but there's also a number pattern, because each of these lines corresponds to a specific wavelength, which corresponds to a specific frequency, which corresponds to a specific energy. So if I look at the wavelength pattern, I look at the frequency pattern, and I look at the energy pattern, they're the same, basically. And when we see a pattern like that, what is the most concise way of defining a pattern? Do you know the most concise way to define a pattern? A law. And a law is a mathematical equation that defines the pattern. And so you don't have the numbers here, but if you did have the numbers, then we can come up with a law. The law for this, which is an empirical law or a theoretical law. Remember the difference between empirical and theoretical?
Empirical is to do with what's observed.
And empirical is what?
To do with what's observed.
Yeah, what's observed, exactly. Empirical is what's observed. So this mathematical pattern comes from observation, and it's called the Rydberg law. And so we can define this pattern by actually a pretty simple equation. But then we think about the mathematics of that, and we think, after we come up with this, we can use the law to make predictions. And in fact, the Rydberg law can be used to predict all the lines in the visible, all the lines in the infrared, and all the lines in the ultraviolet. And so it's quite a successful law, but then you start thinking about things more deeply. And when you start thinking about things more deeply, then you come up with a... So after a law comes, what? Not theory yet. Hypothesis. Theory comes later. Excuse me. So we see these mathematical patterns here. But one of the things is the mathematical pattern, we read off, this is the wavelength in nanometers. We can read off the wavelengths here and we see the numbers here. This is going from high energy to low energy. In other words, it's going from small wavelength to large wavelength over here. Since wavelength is inversely proportional to energy, but we see this pattern here. If we try to apply the Rydberg law to mercury or neon, mercury and neon also show these discrete energies here. You know, we have allowed energies and forbidden energies. But the mathematical pattern for mercury and neon are different. In other words, the mathematical pattern for hydrogen doesn't work for mercury or neon. But anyway, all we're going to do is we're going to focus on hydrogen. These are called line spectra. Line spectra show distinct energies that are allowed here versus a continuous spectrum. A continuous spectrum is this here. In a continuous spectrum, all the energies are allowed because we have all the colors of the rainbow here. Mm-hmm.
But the fact that there's discrete energies doesn't really explain like the properties that these elements have in order for them to have discrete energies and not react with each other.
Yeah. Yeah, just because they're discrete energies doesn't really explain the properties, but it's actually connected to the properties, as we'll see later. The connection isn't so obvious. We're going to take a look at the connection with the properties pretty soon. But what these line spectra are is we don't have to know the origin. We don't have to know quantum mechanics. We just treat these. Each time you measure hydrogen, it always looks like this. Mercury this, neon this. Neon, if you combine all these colors, you get that kind of orange-red neon lamp glow. If you've seen a neon light, although neon lights aren't as common as they used to be, but they used to be quite common, especially at stores. Nowadays, people don't need neon. They used to have glass blowers. You know, these glass blowers would blow glass tube and then fill these tubes with neon gas and then put a little lightning bolt through there. And then you'd have this glowing neon lamp. But you know, I guess nowadays you could use LEDs or whatnot. You get the same effect. But what we say is, even though we don't know necessarily the origin, we could use these as fingerprints. In fact, you could use these as fingerprints to ID the elements. So if you look at the solar spectrum from the sun, the solar spectrum is white light, but it turns out not all the colors are there. You know, there are some colors missing. Some of these colors are due to hydrogen. You know, so we see that there must be hydrogen present in the sun. Some of these colors that are missing are due to helium. You know, if helium is present, it absorbs those energies of light. This is sodium. There's some sodium present, and others. So you can see based on the fingerprints here, we can determine what elements are present there that are being absorbed. But anyway, when you add this up, it's pretty evenly, it's not going to be perfectly white light, but it's going to be awfully close to white light that we see from the sun. That's a solar spectrum there. And so we'll talk about here here we have continuous spectrum. Continuous spectrum, all energies are allowed. And then we have line spectra, or spectrum. Spectrum singular, spectra with an A is plural. If we look at line spectra show that not all energies are allowed. There are allowed energies and forbidden energies. The allowed energies are given by discrete lines. And these discrete lines are allowed. In between the discrete lines, we have forbidden, which are not allowed. Each element has a unique spectrum, and so therefore we call that the fingerprint of the element. Those lines, at least the lines in the hydrogen lamp, arise from these electrons, going from an excited state down to a lower energy state. And so when they get from an excited state to a lower energy state, then the energy has gone down. But first law of thermodynamics says that, or the conservation of energy says that energy is neither created nor destroyed. And so where does that energy go? The energy goes into the surroundings as what we call a photon. A photon is a packet of light. And the photons come in all sizes. There's a continuum of photon energies from red to ultraviolet. No, excuse me, red to violet in the visible region. Or radio waves to gamma rays. And so a gamma photon packs a lot more energy than a radio photon. But they all move at the speed of light. All right, we'll talk about wave-particle duality later. This is kind of mixed up. This slide is really mixed up. It's not really in order. So after pattern and a law, so we have the Rydberg law here. We need a different law for these. But let's just focus on hydrogen. Hydrogen is the simplest element, the simplest atom. So let's take a look at that. And so we have a law. What comes after the law? The hypothesis. So the first hypothesis that came from Bohr. And so this is Bohr's hypothesis. Bohr's hypothesis actually developed into a theory because it was quite successful at predicting the energies of the hydrogen atom, the allowed energies. However, it was unsuccessful at predicting anything else. So the only thing that Bohr theory could predict was the hydrogen atom. Once we go to the next more complicated atom, which would be helium, it failed. And so, in fact, Bohr theory failed for all the elements except for hydrogen. It only worked for hydrogen. But since this is history, we have to talk about Bohr's hypothesis and Bohr's theory. So, all Bohr said was this, that the energy possessed by the electron in a hydrogen atom is quantized versus continuous. And so quantized just means that the energy is limited to discrete values versus if the energy were continuous, then the electron can have any energy. And so this is it. So what Bohr proposed was that the electrons orbit around the nucleus. And as the electrons orbit, they can't have any orbit they want. They could have only discrete orbits that are allowed and nothing in between. And so how do you come up with discrete orbits? Well, one way of thinking about discrete orbits is something like this. Here we could have a continuum of gravitational potential energies. So we could take 1.5 steps up or anything in between. Over here, we don't have a continuum of gravitational potential energies. You know, the higher up we go, the higher energy we get. But here, we could either take 1 step up, but we can't take 1.5 steps up because there's no half step here. Do you see that? And so it's either going to be 1 step, 2 step, 3 steps. Whereas over here, we could take 1 1/3 or whatever we want, 1.1. And so what Bohr is saying is that the electron can't take any orbit it wants. It's only allowed the first orbit. So this would be the first step up. But it can't have 1.5 steps. It has to jump up to the next step, which would be the second step, the third step, the fourth step, etc.
It's only work for hydrogen, right?
Yeah, the mathematics only work for hydrogen, but this was supposed to apply to all atoms. You know, all atoms would have these, what we call orbits. And so what Bohr proposed are these orbits. And these orbits, oops, what's wrong with this? These orbits are discrete. That is, there are certain orbits that are allowed. The allowed orbits are given by a number designation, which we'll call n. N, it could be the first orbit, the second orbit, the third orbit. But we can't have anything between. So for example, an n equals 1.1 is forbidden. But we can have, actually, it's kind of weird to think about, but we can have the 5th orbit, the 6th orbit, the 7th orbit, all the way up to n equals infinity. So the weird thing about this is how many orbits are allowed according to Bohr. According to Bohr, there are an infinite number of orbits allowed. But if there's an infinite number of orbits allowed, then is anything forbidden? Yeah, there's an infinite number of forbidden orbits as well. And so you have an infinite number of allowed orbits and an infinite number of forbidden orbits. Isn't that weird? And so it seems as if there were an infinite number of allowed orbits. Shouldn't all orbits be allowed? And it turns out it's not the case. It's not the case because if I tried to do, again, 1.5 steps, it doesn't quite make it, and it drops back down. So these are the allowed. And that's kind of weird because if you have an electron orbiting around the nucleus, all we say is just give it a little bit more speed. And so let's say it's moving this fast. In order to orbit a little bit farther out, it had to just move it a little faster. The faster it moves, the further away it gets. And so the weird thing is the electron can be moving at this speed, but it can't be moving at any speed between these. And then once we hit here, then the electron can move at this speed. And so it's weird because, you know, let's say the first one is like 15 miles an hour and the next one is like 18 miles an hour, but you can't have anything in between. So if you try to go 17 miles an hour or 16 miles an hour, those are forbidden. And so the question comes up, why is that? And you know what Bohr's answer was? I'm sorry? Okay. Because
Because he created it.
Because he created it, heard of a postulate? Postulate?
Sounds familiar.
Postulate is just taken without proof. And so he just postulated that this is the case. The proof is, well, it fits. The model fits. So there must be some reason, but he doesn't exactly say what the reason is. And so that's just the way nature behaves. That's proof enough. Okay.
Then how would the electrons accelerate? Like if it cannot be at its...
It has to hit a certain amount of energy, then it goes.
Okay, so
But if
stays
it
until-
doesn't hit that energy, then nothing happens. It just stays still. It kind of stays still, and then once you hit that energy, boom, it goes to the next level. And so what you have to do is you have to hit just that right energy to kick it up the next level. If it isn't just the right energy, nothing happens.
But then it didn't work for other atoms.
Yeah, but we're going to talk about the Bohr model because it was semi-successful, but it turned out to be wrong. Well, let's talk about Bohr orbits for right now. So the electrons can jump up or jump down the levels. And so what Bohr did was he said this. If the electron goes from, let's say, the first orbit to the second orbit, then it absorbs UV. A UV photon is required for this. And if an electron is excited in the second level and drops back down to the first, it emits UV. So this can absorb UV or emit UV, and the amount of energy would be the same. That is, the amount of UV energy absorbed is equal to the amount of UV energy emitted. Here. And then if we go from the first floor to the third floor, that's even higher energy UV. And so what this is going to do is going to give us lines in the UV spectrum. But we don't have to go like from the first floor always. We can go from other floors to other floors. So for example, let's say an electron got promoted to the third floor. And so if an electron got promoted to the third floor here, but didn't drop all the way back down to the first floor. Let's say the electron got promoted to the first floor, the third floor. And so we have an electron here on the third floor, but it only drops to the second floor. If the electron drops from the third floor to the second floor, then we get a red photon emitted. If the electron got promoted to the fourth orbit and it drops back down to the second, not all the way to the first. If it drops all the way to the first, that gives us a UV photon. But this is going to be a little higher energy photon. A little higher energy photon means shorter wavelength, higher frequency. And we end up with a green photon here. Then if we go from the fifth, let's go to the fifth here, orbit. The fifth orbit would be n equals 5. This is the next allowed floor. Then we end up dropping from the fifth floor to the second floor. If we do that drop, we end up getting a blue photon. If we go from the sixth floor sixth floor all the way down to the second floor, we end up getting a violet photon. What do you think happens if we go from the seventh floor to the second floor? UV, ultraviolet, exactly. Good. So if we go from the seventh floor down to the second floor, we'll get ultraviolet. If we go from the seventh floor down to the first, we get ultraviolet. What do you think happens if we go from the 4th floor to the 3rd floor? If we go from the 4th floor to the 3rd floor, do you know what we get? Infrared. So by mapping out these orbits, we can map out the entire line spectrum from the infrared to the ultraviolet for the hydrogen atom. And in that sense, the Bohr model was very successful because it predicted the mathematics of this. In other words, the energy here was given by a very simple equation. The energy is given by E sub n, n's what the energy depends on, is equal to 1 over n squared times E1. So the first floor energy is n is equal to 1, and we get E1. E1 is this here, minus 2.179 times 10 to the minus 18 joules. This is our E1. This is our E2, the energy of the second orbit. E2 is equal to 1 over 2 squared times E1. And so if we take 1/4 of E1, that's this. E3 is equal to 1 over 3 cubed, or 1/9, or 3 squared, sorry, 3 squared E1. So if we take 1/9 of E1, then we get E3. This is a mathematical pattern that we see. The 4th floor is given by this energy here, E4. This is going to be 1 over 4 squared times E1, 1/16. So we take this, divided by 16, we get that. And so we see the mathematical pattern in the energies here. And we also see the radii. It looks like the radius is the same, but it's a bit tricky here. The radius is growing quite fast. And so the radii, these are times 10 to the minus 10 meters, or angstroms. There's 0.5292 angstroms, or times 10 to the minus 10 meters. And this we call R1. This is R2. This is R3. This is R4. It turns out the mathematical, do you see a mathematical pattern in the numbers here? Sometimes it's not so easy to see these mathematical patterns, but the mathematical pattern goes like this. R to the n is equal to n squared R1. So R1 is 1 squared times R1, which is just R1. R2 is equal to n squared. This would be 2 squared times R1. So 4 times R1 gives us this. So 4 times 0.5 gives us about 2. R3 is 3 squared R1. So this would be 9 times R1. R4 is 4 squared R1. So an interesting thing happens here, and that is these orbits get further and further apart, so it's hard to see. This is R1, so R2 is going to be 4 times the distance. R3 is going to be 9 times the distance. R4 is going to be 16 times the distance, but this isn't written correctly to scale. This is way off scale, because the second one's going to be 4 times the distance. The third one is going to be 9 times the distance. The fourth one is going to be 16 times the distance. So what we're seeing with the orbits is the orbits are diverging. The biggest orbit possible is R infinity. R infinity is equal to infinity squared times R1. And that's going to be infinite meters out. If an electron is infinite meters out, actually infinite squared meters out, how far away is that? Well, it's infinitely far away. And so what we say is when the electron's infinitely far away from the nucleus, it's been ionized. And so this corresponds to ionization, that is knocking the electron off the atom. And so what we end up forming is an H plus an electron that's infinitely far away. And so the orbits diverge. That is, the orbits get further and further out. But the energies converge because the highest energy we can have is E infinity. And E of infinity is going to be 1 over infinity squared times E1. What is 1 over infinity squared? 0. And so the highest energy we're going to get is 0 joules. And so the orbits diverge. They're getting bigger and bigger, but the energies are converging. This. And so we show that in different ways. What we do is we could draw an energy level diagram. In the lowest energy here we're going to have is E1. It's the lowest energy possible. And that's going to correspond to some orbit here. And then the next higher energy is going to be E2, which would be 1/4 E1. E2. And then E3, which is 1/9. E4, 1/16. E5, 1/25. E6, 1/36. And so what happens is these get closer and closer and bunch up. And we have to fit an infinite number of lines from minus 2.179 times 10 to the minus 18 to 0. And so this is E infinity here. Pretty soon the lines get so tightly spaced it's hard to see the difference. Whereas the orbits, well, this is our first, and then our second will be 4 times. Our third would be 9 times. Our fourth would be 16 times, which is already off the page. And so these are going to be diverging orbits.
What do the energy levels converge?
They converge to 0
Okay,
joules.
what?
The orbits are going to diverge to infinite. One reason why is it's because of how energies are defined. This is the energy of the electron in an atom. And so if the electron's been completely separated, it doesn't mean the electron has 0 energy. The electron's still going to have energy, because energy is the sum of potential. We're just looking at the energy of the electron in an atom. And so if the electron's completely separated from the atom, then we say it's 0 energy. As we bring the electron closer and closer, it becomes more and more stable because the positive and negative attract.
What kind of energy is that? Will it be potential energy?
Yeah, potential energy, exactly.
So as it goes out, it has even less and less potential energy. Like
No, it has higher and higher potential energy.
Oh.
Yeah.
But it's
The highest
zero.
potential, that's because it's 0. E1 is negative.
So there's nothing, meaning that there's infinite amount of energy that could be produced.
There's energy there, but there's no energy in respect to the atom. So we go from -2 to 0. So 0 is the highest energy. But there's still energy there. We're just looking at the potential energy of the electron within an atom itself. It's kind of weird. You don't have to worry about it because our book doesn't cover the energies at all. In Chem 1A, we cover the energies. The radius is an absolute 0. If you're absolute 0 with the radius, you're right at the center. This is what we call an arbitrary or defined 0 here. This is just defined as 0. So the mathematics here is when we're looking at electrons transitioning, let's say n equals 3 to n equals 2, we could model that by looking at the energy change, delta E. Delta E is just equal to minus E1 1 over n final squared minus 1 over n initial squared. This is the Rydberg equation here. And so we could use this Rydberg equation to calculate all these here. So this is a Bohr model of the hydrogen atom. Excited electrons are unstable, they'll fall back and do that. All right, think about that for a moment. So the Bohr model was pretty successful at describing what's happening with the line spectrum. We end up getting a line spectrum because not all orbits are allowed. Why are not all orbits allowed? The answer is because not all orbits are allowed. So it's a little bit circular. It's circular basically because that's the way nature is. Not all orbits are allowed. However, although it was successful explaining hydrogen due to these transitions, so first floor to second floor is ultraviolet. And it turns out that this is the amount of energy. We have two different ways of looking at the energy here. One is per atom. When we look at the energy per atom, it's extremely small. Let's take a look here. These are extremely small energies. When we look, it's times 10 to the minus 18 joules. That's per atom, these energies that we're looking at here. But when we look at it per mole of atoms, then the energies could become quite a bit larger. So what was 10 to the minus 18 joules per atom becomes like kilojoules per mole. And so 2.179 times 10 to the minus 18 joules per atom becomes over 2,000 kilojoules per mole of atoms. And that's how much energy it takes to knock the electron off a hydrogen atom. But anyway, this is showing the electronic transitions. So we could have absorption of energy, which results in an excited electron, and we can have emission of energy, which the excited electron drops back down to a lower energy state. The lowest energy state for the electron is called the ground state. And it might not be on the first floor. It depends on how crowded the first floor is. So those are important contributions. However, there was one major problem with Bohr theory, and what was that? Well, theories have to do two things. Theory has to provide a fundamental description of what's going on. So Bohr did that. The fundamental description of what's going on is you have these orbits. But in addition to providing a fundamental description, a theory should be able to do what? Predict. The Bohr theory couldn't predict anything other than what we call one electron, species like hydrogen. And so, unfortunately, the Bohr theory wasn't long-lived. And the Bohr theory was replaced by quantum. So if we take some parts of the Bohr theory and then we add two important developments since Bohr. One is de Broglie. You don't need to know de Broglie. But what de Broglie had in his equation, the physics that he had, was something called wave particle duality. One, light has this. Light has a wave-particle duality. And the wave-particle duality is not only the gamma ray, gamma rays have shorter wavelength, higher frequency, and higher energy than red light. They also pack a more energetic particle, which we call a photon. And so light has this duality. We have the wave, and the particle part is photon. Photons aren't particles in the sense that they have mass like an electron. Photons are massless, but this is the duality here. We have the wave and the photon duality of light. But it turns out that matter also has this. And so matter, we think of particles of matter, no problem. However, we don't typically think of the wave properties of the electron or whatever matter we're looking at. And so let's take a look at this in more detail. So if I take a baseball, for example, let me do this on another slide maybe. If I look at a baseball, do baseballs show wave properties? If you were to throw a baseball, does it oscillate? No, it doesn't seem to be oscillating at all. So let's say I threw a baseball and the baseball is going at 60 miles an hour. Are any speeds allowed? So, for example, could you throw the baseball at 59.9 miles an hour? Is that allowed or is that forbidden? Is it forbidden or is it allowed? It's allowed. In fact, all speeds are allowed, right? Yeah. From 0 to 60 miles an hour and beyond. I don't think I could throw it at 60 miles an hour, but if I could, all speeds would be allowed. But it turns out that the baseball does have wave properties. It's just the wavelength is so small. Now, this is a different kind of wave. This is not electromagnetic waves. If the wavelength were this small, an electromagnetic wave, then it'd be like gamma radiation, but it's not, or higher. And so lambda, the wavelength of the matter, that is the baseball, is exceedingly small, negligible. So we don't worry about the wave properties. So we don't worry. In fact, we don't even notice. We don't notice the wave properties.
Because what's negligible? What's negligible?
The wavelength of this is negligible. And so this is like thinking of this. Let's say you have an orca or killer whale or something. You have a killer whale in the ocean, and we think about the wavelength of the wave properties of the tail. You know, the tail of the orca is going back and forth, right? And so if the orca is in the ocean, then the wavelength of the kicks here are small compared to the ocean. So if it's going a little faster, it's kicking a little faster, it's higher frequency. Or if it's going a little slower, lower frequency. But can the orca move at any speed it wants in the open ocean? Yeah. In the open ocean, the whale can move at any speed it wants. Okay, electrons also have wave properties. And the electron would be like the orca, you know, this is a lot smaller. But let's say I have a chunk of metal. And if I have a piece of metal here, then one way of visualizing electrons in a metal is electrons are like the ocean, and electrons are free to move throughout the ocean here. And so if the electron moves in the metal, then the electrons can move at any speed. So if it wants to move a little slower, fine. If it wants to move a little faster, fine. Are there any forbidden speeds for the electron moving through there? No, it could go whatever speed it wants, up to a certain limit. But now let's confine it. Let's instead, we're going to put the orca, not in the ocean, but we're going to put it in a tiny aquarium in San Diego, let's say. If we put the orca in a tiny aquarium in San Diego, can the orca move at any speed it wants? No, all of a sudden it's restricted. Maybe it gets 2 kicks from its tail and then it's on the other side of the aquarium. And so in this case, now the wavelength plays a big role because out in the open ocean it could kick really fast, it could kick really slow, it could kick any speed it wants. But now when it's stuck in this aquarium, it can't kick any speed it wants. It's going to be restricted. And what we have to do is we have to get with an electron, we're limited. Each kick has to be the same. And so the orca might get 2 kicks out of the tail and then it's on the other side. Okay. Now, the same thing. Rather than confining an electron to a metal bar or metal chunk or metal filament, we confine the electron to an atom. Now we have to worry about how many kicks of the electron we're going to get in the atom. And so what we're going to do is we're going to confine the electron into a small box. And the small box is called an atom. And so this is called particle in a box. Electron in a box. And the box is an atom. This is like trying to put a whale inside an aquarium. Right? Now we got to worry about things. Whereas a whale in the ocean, no big deal. So when we have a large object like this and the electron's free, then we don't worry about quantization. In fact, we expect a continuum. Over here, when we confine things to a small space, then we have to worry about quantization. That is, we're going to have discrete energies that are allowed and forbidden. The place we see this is another way of thinking about this quantization is we take a string. And we look at how the string can vibrate. And so what we'll do is we'll put a string and connect it here between 2 points. Versus, okay, I'm going to put a string and connect it one side to, let's say, the US, the other side to China. When I pluck this string, I pretty much can get any kind of vibration. It's this huge long string here. But when I pluck this string, it's more confined. And what happens here is when I pluck this string, I could have it vibrate like this. And what we see is what we can see is there's going to be a half a wavelength. A full wavelength will look like this. And so if I pluck this with more energy, then the next allowed energy is going to be here. So this is a half wavelength here, and this is another half wavelength here. And so what we end up with is we end up with 2 half wavelengths. And so here we have 1 half wavelength Here we're going to have 2 half wavelengths. But can we have 1.5 wavelengths? It turns out we can't have 1.5 wavelengths. That would be forbidden. Because 1.5 wavelengths is going to look like, I don't know my red. 1.5 wavelengths would look something like this, where it doesn't attach to the correct place. So 1.5 is forbidden. The string won't vibrate at that level. The next allowed vibration for the string would be 3 half wavelengths here. So 3 half wavelengths are going to be like this, where we need to start and stop at the end, same spots. And so this is going to be 3 half wavelengths here. And so we have to be able to fit in another half wavelength, otherwise we aren't going to end at where the string needs to mount. It needs to mount here and here. But when the wavelength is so small, let's say here there is 1 trillion half wavelengths, because the wavelength is so small compared to the size of the box. This is such a gigantic box. If I have 1 trillion half wavelengths here, the next allowed one will be 1,000,000,001 half wavelengths. Do you think there's a large energy difference between having 1 trillion and 1,000,000,001? This is like if you had 1 trillion pennies, you know, are you going to worry if you have if you lost one of those? Will it make any big? No. And it's barely any difference. If you lose a penny, you gain a penny, it's no big deal if you have 1 trillion pennies. But if you only have one, you know, then it's a big deal, you know. If you have 1 penny, then can you have a half a penny or 1.5 pennies? No, you could have 2 pennies, 3 pennies here. And there it makes a more significant difference. Because if you only have 1 penny, you know, then the impact is much more. Versus if you have 1 trillion, then this is like the baseball. The baseball can go any speed because the next allowed speed is putting 1.5 trillion. Or it could go slower. You know, 299,999,000 half wavelengths. You know, something like that. So we don't really see this as an issue because for matter, because the wavelengths are so small. But in this case, the lambda is not negligible. So when the box gets small, lambda is significant. Lambda of matter significant. It's significant because of the dimensions of the container. So some people say quantum mechanics deals with very small things. Well, quantum mechanics deals with both small and large things, but it becomes significant for small things. It's kind of negligible for large things.
That was good to watch.
De Broglie. De Broglie. So, these are called standing waves. Standing waves are quantized. They're forbidden. Like if you have a musical instrument, they're going to be forbidden. And so this would be the fundamental, this would be like the first overtone, second overtone. But anything in between is forbidden. It just won't vibrate at that frequency. This goes for lots of different things. These are called one-dimensional standing waves. We could take a look at two-dimensional standing waves here. This is a metal plate, It's an XY two-dimensional metal plate. And the waves we can generate on this metal plate are like a drum. You know, they're going to be forbidden and allowed. I don't know if this is the best video. This one looks more interesting. This is a speaker. Look at the vibration of the speaker. Do you see the standing wave in the speaker? Pretty wild. Let's do this. So we're just going to watch this video. Turn on the sound. They don't start from the lowest. We're just jumping into the middle of this.
The first experiment for the Cymatics music video is basically a metal
This is the wrong one, I think.
plate attached to the
This is the right one. So this is forbidden, 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 allowed. So this is the one of the allowed energies. And this is the wave, this is sand particles. So the sand particles are going to collect in the troughs of the wave. And so this is what we call positive amplitude, and then it drops down to negative amplitude. The sand particles collect there. Then it goes back up to positive amplitude, like a regular wave. You expect these changes in amplitude here. And so we can see this would be a two-dimensional. So this is an allowed vibration of the plate. And then what they're doing is they're scanning all the energies. So listen to the tone, and you'll see that these other energies are forbidden. So it's kind of forbidden, 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 as they're increasing the energy. It's not being absorbed. So it's cycling. This would be that was the next allowed. This would be the next allowed. And forbidden, 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 allowed. Forbidden, 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 allowed. The waveforms become more and more complex. You see that as the energies go up. There are a lot more of these lobes and nodes, we call them. So just like other things, well, it's going to depend on the size of the plate, what material it's made out of, this kind of stuff. But we're going to see that the plate, the vibrations of the plate are also quantized. And of course, the bigger the plate, the less. We can have very big objects, like the Tacoma Narrows Bridge. Let's see if I have that. You know, nowadays when you do construction, you look at you have to look at the allowed frequencies for big objects like the bridge. So they just cut this, and then a short time later, there are some winds, and the winds were hitting this at just the right frequency. This is an allowed energy of the bridge here, and the winds were just at the right energy. And then eventually what happened was there was enough energy that the bridge fell apart. Have you seen this? This is very classic in physics. So nowadays what they do is they try to measure the allowed frequencies for these structures and make sure that when the wind passes by or whatever, you're not going to hit that frequency. Let's say an earthquake. You don't want an allowed frequency to be like an earthquake frequency. Otherwise, you're going to ask for trouble. It's going to absorb that and cause it to what we call resonate. In other words, these frequencies, these allowed frequencies, are called resonance frequencies for these. And so when we look at the allowed waves for an electron, it's three-dimensional. And so if we consider the wave properties of an electron, actually there's one more. This is what it looks like. You know, it kind of looks like the 2D. These are 2D, but this is spread out into 3 dimensions. So this is what the electron. And so we have, these are allowed, everything else is forbidden. And each of these has a specific energy associated with it. Here. And so what we end up with is Bohr just said that the energies are quantized because the energies are quantized. It's a postulate. It's taken without proof. Whereas with de Broglie, we can see that quantization of energy comes out naturally. Here. So that's the first thing that was incorporated. So we take aspects of the Bohr theory and add de Broglie's wave-particle duality. And then we add one more thing. We add the Heisenberg uncertainty principle. The Heisenberg uncertainty principle just says this. There's going to be uncertainty. And the way we use it, it's a little bit more complicated than this, but I'm just going to go straight to how we use it. How we use it is we pinpoint the energy of the electron. What do we want to know about the electron? We want to know two things about the electron. One is its energy. And so in the Heisenberg uncertainty principle, we pinpoint the energy. But if we pinpoint the energy, what it means is that the position, we'd like to know where the electron is. So if we pinpoint the energy, the position cannot be pinpointed. Instead, what we get is a probability. Defining the position. And so the way we think about Heisenberg, this would be de Broglie here. The way we think about Heisenberg is like this. We think in terms of electron clouds. There's an analogy that people use, and this is a bird analogy. Let's say the nucleus is the nest for the bird. And let's say the bird, you know the energy of the bird. The bird ate breakfast, let's say, and has a certain amount of energy. And let's say the bird's position is here. Can you tell me in 5 minutes where the bird is going to be? No, you can't. But we know how much energy the bird has. Like, so for example, the bird's here, but do you think the bird is, let's say, in Torrance, but do you think 5 minutes later the bird will be in Europe? No, there's going to be very low probability for that, right? Electron could be, but the probability would be extremely low. But maybe we measure it and the bird's here. And so we could pinpoint the electron here, 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 here. And so if we keep measuring the position of the bird, we're going to see that the bird, because of its energy, can't get too far from its nest. Once in a while, it's farther out. But most of the time, it's going to be within a certain range of the nest. Of course, as the bird had more energy, then it could venture further out. And so what this results in is what we call an electron cloud. The electron cloud is going to be described by dots. These dots show what we call a probability for finding an electron. And so the most probable areas for the bird are going to be close to the nest, maybe right at the nest. And as we get further and further away from the nest, the probability diminishes. But the bird can sometimes be found very far out from the nest. And there's no limit. Although the bird could be infinitely far away, the probability of that is very, very small. And so what we do is we draw a boundary here. And we're going to say that 95% of the time, the bird is within this imaginary boundary or imaginary fence. And so this is called the 95% boundary here. So there's a 5% chance of finding the bird outside. In other words, 5% of the green dots lie outside. 95% of the green dots lie inside this boundary. Now, if the bird had more energy, then this 95% boundary expands. If the bird has less energy, the 95% boundary shrinks. And so this is what we call an electron cloud. The electron's the same. So if we have a nucleus here, then where's the electron? Well, it depends on the energy of the electron. At the lowest energy, the electron is expected to be like this. And then if we look at 95% of the dots, we'll come up with a 95% boundary. Like that. And so this is the electron cloud. So if we take these two ideas and combine it with the Schrödinger equation, combine it with de Broglie, we end up with the new physics here. And we get the Schrödinger equation. This new physics is called quantum physics, and at the heart of quantum physics is the Schrödinger equation here, which factors in the wave-particle duality in Heisenberg. From the Schrödinger equation, we can figure out what the allowed states for the electron are. The allowed states, we call these orbitals. Orbitals are different than orbits. And so the contribution of Niels Bohr, the whole idea of orbits has been abandoned. Orbits turn out to be wrong. And the orbits are replaced by orbitals. And so the whole thinking about electrons orbiting the nucleus is completely wrong, because the bird, it's like the bird doesn't fly in an orbit around the nest. So when you're looking at a bird, this is Bohr. Bohr says the bird is just orbiting. And it'll orbit this distance from the nest, and the next distance will be here 4 times the distance away. But the bird can't fly closer, and the bird can't fly farther from the nest. It has to just orbit around one of these. And then we can figure out where the bird is at any time. So if the bird is just going in circles like this at some constant speed, then we can predict where the bird's going to be 5 minutes later. It's not going to be a problem. And so from the Schrodinger equation, we get the allowed states. So what we're going to do is we're not going to do the math. We're going to look at the mathematical restrictions. There's a pattern to this. And so what we're going to do is we're going to look at the pattern here that's observed for the orbitals. It's a mathematical pattern. And so we don't have to do all the math of the Schrodinger equation. We're just going to figure out the mathematical pattern in the orbitals. Okay, so we'll take a break here and then we'll start up again. So the pattern, this mathematical pattern, is a number pattern. And this, it depends on three numbers. The three numbers are given letter designations for the variables. There's N, L, and M. N, L, and M will tell us the allowed states for the electron. So let's take a look at the number pattern here. And so the quantum mechanical model of the atom comes from the Schrodinger equation. And it says that it relies on four numbers here. But for the allowed state, we rely on three numbers. The three numbers are going to be N. N is called the principal energy level. And L, which is the sublevel for the shape. So this is the energy. The shape.
What's N?
The energy, or the principal energy level. It's what step you're on. So first step, second step, etc. And the number of each shape is M. And so we have N, L, and M that designates it. So the answers to the Schrodinger equation are called psi. This is the symbol psi, and it depends on N, L, and M. These are called wave functions, or orbitals. And these are the solution to the Schrodinger equation. In order to be a solution to the Schrodinger equation, there are mathematical restrictions that are observed on the quantum numbers. So for example, N, these are the allowed values of N. 1, 2, 3, all the way up to infinity. So there are infinite allowed values for N, but there are also an infinite number of forbidden ones. So for example, 1.1 is forbidden. L will contain all values from 0, 1, ... to a max of N minus 1. So if N is equal to 1, then there's only one allowed L value, and that's 0. Because the max N minus 1 is 0. 1 minus 1 is 0. If L is equal to 2, then there are 2 allowed values of L, 0 and 1. If n is equal to 3, there are 3 allowed values, 0, 1, 2. This tells us the shape. We have different ways of describing the shape. One is we give it a letter designation. So for example, if we have a 0, we call it an S-type orbital. If we have a 1, we call it a P. If we have a 2, it's D, etc. SPD. That's a letter designation instead of a number designation. The numbers come from the quantum mechanics, the Schrodinger equation. M depends on L. And so it takes on all values from minus M, excuse me, not minus M, minus L. Let me fix that. From minus L to plus L, going through 0. So we have minus L plus 1, dot, 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 through 0, through L minus 1 to L. Now there should be another dot, dot, dot here. So depending on the L value, if L equals 0, then we only have one M value. It's 0 because we go from minus 0 to 0, that's only one value, 0. If L is equal to 1, then we have 3 values. Minus 1, 0, and positive 1. If L is equal to 2, then we have 5 values available. Minus 2, minus 1, 0, plus 1, plus 2. So these are all integer values. And so it turns out that there are an infinite number of allowed states. Just like there are an infinite number of orbits in the Bohr model, there are an infinite number of orbitals for the hydrogen atom. And the easiest way to describe the infinite number is not one by one. It would be impossible to describe them one by one. Instead, what we do is we describe them based on their mathematical restrictions. So we can derive all infinite orbitals for this. Our book doesn't go through it in much detail, and therefore we have to supplement the book. So if you go to the supplement, let's say after nomenclature comes quantum numbers and electronic structure. It's called quantum 1. So quantum 1, we have the Schrodinger equation, or Schrodinger's wave equation. And we have the answers to the Schrodinger equation called orbitals. And the orbitals are going to depend on these quantum numbers. 3. And so what we want to do is we want to generate all the orbitals. Not all, because it would be too much. We want to start generating the orbitals, just like we generated the orbits. The orbits for Bohr are easy. You have the first orbit, second orbit. And so what are the orbitals going to be like? So the orbitals are going to depend on 3 quantum numbers. The principal quantum number, the principal energy level, n, basically tells us the energy, what floor we're on. We have this one, the L, the azimuthal quantum number, which tells us the shape, the orbital shape here. And so L equals 0. 0 is a spherical shape. And L equals 1 has a dumbbell shape. L equals 2 is like a 4-leaf clover. L equals 3 is more complex. And this gets more and more complex, like the standing waves on a 2D plate. This goes up to max, so this takes on all values up to a max of n minus 1. And then there are different numbers. So for example, if we're here, which we call S, then there's only one orbital. But if we're here, which we call P, there are 3 orbitals. And so we call these sublevels. And so this is our energy level, and we have energy sublevels. The S sublevel, the P sublevel, the D sublevel, or the L equals 0, the L equals 1, L equals 2 sublevels within that level. In each sublevel, we'll have different numbers of orbitals. The number of orbitals are going to be given by M. M is a function of L. That's why they wrote M sub L here. It's a function of L because it depends on which L. So for each of those sublevels there, we could have a varying number of orbitals. In fact, there are 2L plus 1. For each L, we expect to find 2L plus 1. 2L because we go from negative through positive, and the plus 1 is we add the 0. And so 2 times 0 is 0, plus 1 is 1. So there's only one orbital in the L equals 0. So we can begin to map out the orbitals. I'm not going to cover everything here just yet. But what's the first orbital that we're going to encounter? This is like, what's the first Bohr orbit? Well, the first Bohr orbit is simple. The first orbital we're going to encounter is the n equals 1. If n equals 1, then the possible L values are all from 0 to n minus 1. So there'll be only one. And then this is going to range from minus L to plus L, so there's only one value here. So we have the 1, 0, 0 orbital, we call it. The next allowed orbital is n equals 2. When we have n equals 2, then there are two possible L values. The two possible L values is L equals 0, as before, and L equals 1. But L equals 2 is forbidden. L equals 2 would exceed the max allowed L value. And so we have two sublevels. Here we only have one sublevel. When we have n equals 3, we have three sublevels, 0, 1, and 2. But sublevel 3 is forbidden because that would exceed the max. The max is n minus 1, which would be 2. That's the max. If we're in the 0 sublevel, we only have one orbital. 0 sublevel, one orbital. That is one value of m. When we're at the first, the n equals, not n equals, L equals 1 sublevel, that is, we call this the S, the 0. We call this the P. So when we're at the P sublevel, there are three orbitals corresponding to minus 1, 0, and 1. So the three orbitals here. When we're at the second sublevel, there are 5 orbitals. The 5 orbitals are minus 2, minus 1, 0, minus 1, plus 2. And so by doing this mathematical pattern, we could figure out the entire allowed orbitals for the hydrogen atom. So let me ask you this. If I'm in the 5th energy level, n equals 5, how many sublevels do I have? How many L's? So n equals 5, I'm going to have, well, 0, you got to count 0. So 0, 1, 2, 3, 4, 5 sublevels. There are other patterns here that may not be so obvious. Another pattern here is, if I'm in the 3rd sublevel, how many orbitals do I have total? 1, 2, 3, 4, 5, 6, 7, 8, 9. If I'm in the 2nd energy level, I have how many orbitals? 1, 2, 3, 4. Do you see that pattern? So if I'm in the 5th energy level, how many orbitals? 25. And so we could figure out all 25 of those. And so from these mathematical patterns, we can build the entire orbital scheme for this. And so let's do that. But we're not going to do it for everything. We're just going to do it for a few of these. So I'm going to do this for the H atom. And I'm going to do this in terms of energy. The lowest energy orbital that we're going to have is with the first energy level, n equals 1. So I'll do that over here. So we're going to plot energy on the y here, and we're going to go 1. This is going to be psi 1 0 0. This is n L m. So when n is equal to 1, L can only take on one value, 0, and m can take on one value. So we only have one orbital. The one orbital is shown as this line here. And the shape of this orbital is a sphere. And so it's going to look something like this, where we'll draw the electron cloud, and we'll draw a 95% boundary. And so it looks like this. And so this is the first allowed orbital. The next allowed orbital is going to be with n equals 2. And so let's go up here and do that. We'll have psi 2 0 0. Now the difference between a 1 0 0 and a 2 0 0, 2 0 0 should be a lot bigger. And so if I look at the 95% probability boundary, it looks like this. There's some other structural features that are different. So draw like that. But in addition to the 2 0 0, I can have others. And so this will be a psi 2 1, negative 1, a psi 2 1 0, and a psi 2 1 1. And we can give these letter designations. So for example, a 1 0 0 is called a 1s orbital. A 2 0 0 is called a 2s. However, these two 1s are what we call 2p orbitals. And so one of these we could designate like the 2px, 2py, and 2pz. They're going to be oriented on different axes in three-dimensional space. So we have those. And so here I'm going to divide this by sublevels. And so here we have the n equals 1, we have the n equals 2 energy level, and then over here we have the L equals 0 sublevel, and here we'll have the L equals 1 sublevel. Over here I'll put the L equals 2, but L equals 1 is forbidden in n equals 1. L equals 2 is forbidden in n equals 2. And so we'll have to go up to the third sublevel, the third level. And so here we'll have psi 3 0 0. Be here. This is called the 3s orbital. And then we'll have the 3, I'm going to drop the psi. So this will be the 3 1 negative 1. here. 3, 1, negative 1, 3, 1, 0, and 3, 1, 1. And these we call the 3p orbitals. They're going to be bigger than the 2p orbitals. The 2p orbitals are going to look like this. There's going to be a dumbbell shape along the x-axis, a dumbbell shape along the y-axis, and a dumbbell shape along the z-axis. So these are just going to be bigger. But we also have L equals 2. When L equals 2, we're going to go 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, and 3, 2, 2. So that gives us a total of 5 orbitals in this sub-level. These are sub-levels here for each principal level over here. And these sublevels we call the 3D sublevels here. And these shapes are going to be different. And so these will be like a clover leaf shaped orbitals. And they're usually associated with planes rather than axes. So we'll have the 3dxy, 3dxz, 3dyz, etc. Depending on what plane it's in. All right, so what happens here is this. The quantum mechanical picture is a bit different because in the Bohr model, you know, we have the first orbit, the second orbit, the third orbit. But in quantum mechanics, it's a bit more complicated. It turns out there are a lot of orbitals. The n equals 2, there are 4 orbitals. At n equals 3, there are 9 orbitals, etc. But all these orbitals at the n equals 2 are the same energy because in a hydrogen atom, the energy only depends on n. And so energy is just a function of n. Let's see if I can fix this. Energy is just a function of n. And so n equals 3 for all 9 of these orbitals. And therefore, all 9 of these orbitals have the same energy. And so when we're looking at transitions, it's still the same thing. We're going from n equals 3 to n equals 2, that's the red light. N equals 4 to n equals 2, that's the green light, etc. But the transitions are a bit more complex here because it depends on which orbital we are in the n equals 3 energy level. But the end result is the same as the Bohr model. And so we could go etc. here. Actually, let's just do, there's not enough room to do one more. Now, what happens is this. When we have more than one electron, so that's what we call single electron. If we have multi-electron, go back. Hydrogen atom only has 1 electron. So this is a 1 electron species. When we have multiple electrons, what happens is the electrons interfere with each other. And when the electrons interfere, then the energy turns out to be a function of n primarily and secondarily L. And so the energy is a bit different. And so for multi-electron, what we lose is something called degeneracy here. Let me do this. So we have our 1s orbital here. I'll just write it down here, which is the 1, 0, 0 orbital. And the next energy is going to be the 2s, which is going to be the 2, 0, 0 orbital. Normally the 2s and the 2p are the same, but what happens is when the electrons interact with one another, it splits these 2 sublevels. So now that what's observed is the 2p's at a slightly higher energy. So the 2, 1, negative 1, 2, 1, 0 and the 2, 1, 1 orbitals are slightly higher in energy. However, the 2 1s are all the same. So this 2, 1 is the same as this 2, 1, which is the same as this 2, 1. And so the 2p orbitals are the same. And then we go on to the 3s. 3s are going to be higher in energy. But the 3p are going to be slightly higher in energy than the 3s. And the 3d get kicked way up here. In fact, before the 3d come, we see the 4s. And then finally we see the 3d. The 3d, I'm offsetting to the side because I'm breaking up the sublevels. So this is the L equals 0 sublevel. This is the L equals 1 sublevel. This is the L equals 2 sublevel. So I'll just write it over here. And these are the 3d. The 3d orbitals are going to have these quantum numbers. They're going to have 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, and 3, 2, 2. That gives us 5 3d orbitals. And then we end up with the 4p orbitals next here. But where are the 4d orbitals? The 4d orbitals turn out to go into the next, way up here, next level. And so what we're going to do is we're going to come up with something called shells of orbitals. So I'll color the shells differently here. So the shells are going to be orbitals with closely spaced energies. So this is the first shell of orbitals. This is the second shell. This will be the third shell. Now the third shell doesn't contain all the n equals 3 orbitals. We only see in the third shell the 3s and the 3p. The 3d actually end up in the next shell, which is the fourth shell. And the 4d end up in the fifth shell. And so the pattern here, there's a pattern to the shells. In the pattern of the shells, we build a little pyramid like this: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, etc. And the way we do the shells is like this here. Mm-hmm.
Is F the highest out of the 4 2, or does it?
No, it goes higher. Once we go past F, it goes alphabetical. So it goes S, P, D, F, and then it comes after F. G, H, I, K, L, M, N, O, P, then it goes double.
Okay.
Each shell begins with an s orbital. And so this would be the first shell here. Maybe I should do that in yellow. Match. The first shell. The second shell I'll do in green here. The second shell will be 2s, followed by the 2p. Stops here. Third shell I'll do in blue here. Third shell starts with a 3s, and then goes 3p, and then stops here. And then the fourth shell starts with 4s, and then goes to 3d, and then 4p, and then stops here. So we can use this shell pattern here to figure out what orbitals belong to each cell. In other words, what we call these subshells, or sublevels belong to each shell. So,
Like in the fifth shell, it doesn't have 4f.
yep. The fifth shell does not have 4f, exactly. The fifth shell, if we were to do the fifth shell, it would have 5s, 4d, 5p, and stop there. That would be the fifth shell. And we would continue on. So what we want to do is we want to be able to draw the, this is called the energy level diagram for multi-electron species. We want to be able to draw this here, so that it looks like this. You see the fifth shell here? Do you see the sixth shell? We want to draw the first four shells of a multi-electron atom. This is like trying to draw. Now, do you see how much more complicated the transitions are going to be here? Because there are a lot more levels. With a lot more levels, we're going to get a lot more line compared to hydrogen atom. And so using this, we can describe the spectra of helium, lithium, anything with more than one electron. There. And so we should learn this here. At least learn how to draw this. Do you see this energy level diagram here? Don't learn this energy level diagram here. It's pretty worthless. So this figure 1114, completely ignore it. Instead, look at the lab supplement. Because what we're dealing here now are not orbits, but we're dealing with orbitals. This would be representing maybe one orbital here, and the dots represent the probability. The greater the density of dots, the more probable it is to find it there. And the further out we go, the less probable. And what do these orbitals look like? This is what the orbitals look like. And so this is an L equals 0, or an S orbital. This is an L equals 1. When we have L equals 1, then M can be -1, 0, and +1. So we have 3 types. This would be an L equals 2 or D orbital. An L equals 3 would be an F orbital. An L equals 4 would be a G orbital, etc. And so these are the D or the L equals 2. So we're going to have 2 -2, 2 -1, 2 0, 2 1, 2 2 for L and M. And then we put the principal. So it could be third, 3D, it could be 4D. There's no such thing as 2D because that would be forbidden, or 1D is forbidden as well. And so these are the shapes. Usually people remember just these first. The simplest, which is the sphere, L equals 0, and the dumbbell, which is the L equals 1, or the p orbitals. D orbitals are getting more complex, so you don't have to worry about those. When we're at 1s, that's the lowest energy. This is the smallest. When we get to higher energies, the electron could be further away. So this is 2s, 3s, etc. So we just grow bigger and bigger. These orbitals do. All right, I'm going to stop here, and we're going to get some practice with Chapter 10. So this is Chapter 11. I'm not quite done with Chapter 11. I'll finish Chapter 11 next week. And so the practice we're going to get with Chapter 10 will be a standard Chapter 10 calculation, which is what we call a limiting reactant, excess reactant problem. So why don't you give this one a shot? I'm going to give you some cards here. This is an important calculation to know how to do. We do a lot of the limiting reactant, excess reactant. In chemistry. Huh?